Hello! Today we're going to do a little video teaching here on Ohm's law and simple circuits. So I will not be on the camera because my easel isn't that high, so you'll have to look at my just whatever part of me ends up on camera. So, and I hope you can hear me. It looks like you'll be able to hear me okay. Let me get my pen, and here we go. So what we're looking at in this, and that'll focus in. Don't worry about it. What we're looking at is Ohm's law, which relates voltage to current and resistance. And of course, we can manipulate those variables, and we will. But let's just start with the simplest little circuit of all. We just got a little voltage source here, and we got a resistor here, and it goes back around. So it's a circuit now because it has completed, you can run all the way around it. And let's make this a 10 volt DC source. We're not worried about AC right now. And we're going to make this a 10 ohm resistor. So now we can figure out how much current is in there. So we've got the voltage, and the resistance. So we need to rearrange that. And when we do that, we're going to get I equals V over R, which equals 10 volts over 10 ohms, which equals 1 amp. 1 ampere. So that's the simplest way right there. That's the simplest little thing we got to do. Now, the problem is this circuit won't actually do anything. So we got to start thinking about, and we're a long way from doing anything besides maybe lighting a light bulb and adjusting the intensity of the light bulb. And that's something. If you've ever been on a date, you know that being able to adjust the intensity of the light bulb is something. We like dinner with soft lighting. All right, here we go. But that's not what we're doing right here. All right. I'm just going to leave that up there for now. That'll probably have to go off later. So the first thing we're going to do is resistors in series. So this is resistors in series. And series means end to end. So let's draw our same. We're gonna be using this 10 voltage source the whole time. So for resistors in series, they're placed end to end. And when something is in series, you have to go through all the components if you're going to run around the circuit. So that's our 10 volt source, and we're going to label this R1 and R2. Those are good labels for resistors, R1 and R2. And they're each going to be 10 ohms just to start with. All right? So how do we figure out what so we've got this V equals IR. And the first thing we want to do, if we want to figure out how much current is being drawn off this voltage source, we have to figure out what the total resistance is. And for resistors in series, it's very easy. All you do is add them up. So the total resistance on the circuit is going to equal R1 plus R2 plus however many else there are. In our case, it's going to be 10 ohms plus 10 ohms equals 20 ohms. So now, unlike the previous circuit, now there's 20 ohms of resistance. So now we can find out what the current is, because we need to know what the kind of current is getting drawn off this battery. So again, we have the current, I, amperes, equals the voltage over the resistance. And in this case, it's 10 volts divided by 20, that's volts and ohms. So that's going to equal 0.5 amps. And there we go. Not quite. Okay, so the next thing we want to be able to do is say, well, so voltage is potential energy. It's the force, it's the energy potential going on. And this is a 10-volt power source. So the question we have now is, I'm going to just label these different parts of this circuit A, B, and C. Okay, so first of all, assuming the wire is has negligible resistance. Being here on the wire is no different than being connected right here to the power source. So the question now, though, is if we've got 10 volts total, what is the voltage drop from A to B? So what's the voltage drop from A to B? And we know V equals IR. Current, in a series circuit, current stays the same all the way around. So we already know that our current is 0.5 amps. And the voltage equals the current times the resistance. And we're going to put R1. We don't have to put current 1 because in this instance, current's the same all the way around. So that voltage is going to be the current, which is 0.5, times the resistor, R1, which is 10 ohms. So that's going to be a 5-volt drop across here. And then for the other one, since the numbers are exactly the same, we can just do it again. I'll just do it again. But I'm going to do it really fast because all the numbers are exactly the same. Okay, so now it says we have a 5-volt drop here and a 5-volt drop here, which makes perfect sense because we have a 10-volt drop from this point to this point, right? So somewhere throughout this circuit, we have to lose all 10 volts of potential energy. Potential electrical potential. So it's going to be 5 on each. All right, so that's not too bad. Now let's go to 3 resistors, just for some fun. Oh, where's my rag? There's my rag. All right, I'm going to erase the whole thing now. You don't need that. V equals IR. Just remember it. V equals IR. Maybe I'll write it up in the upper right-hand corner over here. I think I will. Just in case you're not remembering it. All right, so V equals IR. That's Ohm's law. All right, so now what we want to do, we're going to go to 3 resistors, and they're all going to have different resistances. And this is where we have to start doing, not a lot. It's going to get trickier when we get to parallel. These are all still series. So let's do our little 10-volt power source over here. And we go like this. And there's a resistor 1, 2, 3. And we have to complete the circuit. Otherwise, the electricity won't flow at all, right? So here's R1, R2, and R3. We're going to label these little parts of the circuit because we want to find out what's going on at each part. Those are just labels. You can use whatever label. You could use different happy faces if you want. But it'd be hard to label a very big circuit with a lot of different happy faces that are distinguishable. All right, so for this one, we're going to make this one, R1 is going to be 5 ohms. R2 is going to be 7 ohms. And R3 is going to be 8 ohms. All right, so the first thing we want to do is find out what the total resistance is, because we need to know that in order to get the current in this setup. So the total resistance, total, is just going to equal R1 plus R2 plus R3. So it's going to equal 5 plus 7 plus 8, which just happens to equal 20 ohms. So now we know the total resistance on the circuit, right? So we can figure out the amperage. So if V equals IR, I equals V over R, which is going to equal the voltage, 10, divided by the resistance, 10 volts, 20 ohms, is going to equal 0.5 amps. Okay? So that's what we got in this instance. When we get to parallel circuits, we're going to start finding different amperage flowing through different areas of the circuit. But that's not yet. So here we go. Let's see. So I'm just going to put 0.5 amps there. So we've got that. Now what we want to do is find out what the voltage drop is across each of these resistors. Because remember, we've got 10 volts that have to, the thing has to drop 10 volts from here to here all together. And so we have to figure out what each of those are. And it's still the same. It's just Ohm's law again. So we're just going to call this voltage drop from A to B equals IR. The current we know, 0.5 over resistor A, 5. So, oh, I just made a very silly mistake, didn't I? I hope you caught that before I did. You should, because you're the one who's thinking along with me, and I'm the one who's having to do this on the fly. So V equals IR, right? Duh. IR. The current in this configuration is always the same, 0.5 amps times this resistor, which is 5 ohms. I'll probably start leaving those off soon. So that's going to equal what? 2.5. So there's a 2.5 volt drop across this resistor. Now what about the B to C? What about across this resistor? Same thing. IR, 0.5 amps times 7 ohms. So that's going to equal 3.5 volts. And right here, the third one, what's the voltage drop from there to there? That is CD. Same thing. IR, 0.5 amps times, what's that? 8 ohms. 8 ohms equals 4 volts. So now we found out what the voltage drop is across each of these resistors. And since it's a 10 volt drop altogether, the voltage drop across each resistor needs to add up to 10. And in fact it does. 2.5 plus 3.5 is what? 6 plus 4 is 10. So there we go. Isn't electricity wonderful and magical? All right, so that is series. Now we have to go to parallel circuits. And we'll start, I think, with this one right here. What did, okay. I do not need to worry about it. Okay. Here we go. Let's erase that and move along. I have to clean this board pretty soon. Or at least launder my eraser. Okay, so let's make a very simple parallel circuit. So now we're going to do, this is a parallel circuit, and then at the end we're going to be combining these together. This is a parallel circuit. That's why I like smart boards. There's an undo. I don't have to grab the rag. All right, so let's do here's our little 10 volt power source. We're just going to keep that the whole time. So in a parallel circuit, your components are all hooked up. You can think of it as like a rail or something like that. So assuming that we have resistance-free wire, this is all superconductor wire of the future. If this is 10 volts across there, you can see these are all just wires. So whether I measure here and here, or here and here, or here and here, or here and here, it's still going to be 10 volts. So in a parallel configuration, the voltage is the thing that ends up staying the same when we're trying to compute what current is going where and things like that. So, but first of all, we have to figure out, let's label these R1 and R2. And we're going to give them, just to make it start easy, we're going to start with 5 ohms. This is just two 5 ohm resistors, like that. And so what we have to do is, because they're both connected to our voltage source over here, what we have to do is figure out what kind of resistance this little system offers this voltage source. I hope that makes sense. This thing is kind of because this voltage source is hooked up to both of them, this is kind of a little system of resistance, and that's what we got to figure out. So this is the one little bit of tricky mathematics. It's not too tricky, but it's a little tricky. So to figure out, if you have resistors in parallel, to figure out the resistance that that parallel system of resistors offers whatever voltage source is coming in, it's pretty simple. It's just 1 over R sum. I should have used sum on the last board too. Oh well. Equals 1 over R1 plus 1 over R2 plus, and on down the line, however many resistors are in that parallel system. And of course, if they're just resistors, all they're doing is resisting. But if they're electrical components of all sorts of different types there might be, then you have to start calculating all this stuff, because you need to make sure enough power is getting to each component for it to do the things that it needs to do, right? But we got to start somewhere, and this is where we're starting. So in this case, we're going to have 1 over our sum equals 1 over 5 plus 1 over 5, which is going to equal what? 2 over 5. So now that we have this, we can just take the reciprocal, and our sum equals 5 over 2, which just happens to equal 2.5 amps. Excuse me. There we go. 2.5 ohms. So you can see that the current that's going through here gets to split off, and half of it goes through there and half of it goes through there. So each of them contributes some resistance, but because the current gets divided in half, there's less resistance to the current because it's got more paths to go through. So now we're going to go and figure out what the current traveling through this circuit is, which is going to be, the current is like the draw on the battery. So if you figure out the amperes, you're going to know how fast that battery is going to drain. So here we go. So we have Ohm's law, V equals IR, right? But now we're trying to find I. So we have I equals V over R equals the voltage we already know, 10 volts, over the resistance that this system offers, 2.5 ohms. So 10 volts over 2.5, where am I? 10 volts over 2. Did I do that right? V equals IR. So no, I did that wrong, didn't I? I equals, no, I did that right. 10 volts divided by 2.5 equals 4 amps. Okay, sorry about that. Oh, I see what I did. I left it as a fraction on my notes, which you can do if you want. You can leave it as fraction, or you can change it to decimal. If you do a decimal, make sure you use at least 2 decimal places, okay? All right, so that's the amperage that's coming through there. So what else do we need to figure out? So because the flow of the electrical power splits right here, some of it goes this way and some of it goes this way. And so the voltage is the same, but the current goes down. So now let's find out the current that's going through resistor 1. Okay, so we got V equals IR. We've always got V equals IR, right? And then we want to find the current going through resistor 1. So the voltage is the same all the way across that rail, for lack of a better word. And now we have R1. R1 is 5 ohms. So we got the 10 volts divided by the resistance, 5 ohms. So the current going through this resistor is going to be 2 amps. And I'm not going to do the other one for the sake of time, but you know it's exactly the same because that's also 5 ohms. And so the R2, V over R2 is the same. It's also 2 amps, which makes good sense because we know the whole system is pumping 4 amps right here. So 2 of them go that way and 2 of them go that way. That's pretty cool, right? So now we got to do another thing, which is have a circuit with 2 different resistors. And this is where we start to get, well, it depends on what you think. I think it's fun. Some of you might not. I hope you do, though. And maybe in honors physics we can design a computer circuit or something. That would be fun. Okay, we're still doing parallel circuits. I'm going to erase it for the sake of room. All right, so we have our 10-volt power source as always, and we're going to have 2 resistors. There's a rail and a resistor, and it goes like that, and then we're going to have another resistor right here. We're going to call this one R1 and this one R2. That's always good. And we're going to make this one 3 ohms and this one 7 ohms. Now it gets interesting, doesn't it? All right. So the first thing we need to figure out, we've got a little system here that is offering resistance to this voltage potential. The power moving, the electricity flowing across, moving from one end to the other, because that's a potential that wants to equal itself out, right? So we have 1 over R sum equals 1 over R1 plus 1 over R2 equals 1 over 3 plus 1 over 7. Now you get to go back to Algebra 1. Actually, it's probably not even Algebra 1. I don't know how the math delineates in the lower grades, but we're going for common denominators. And the easiest way is to multiply the top and the bottom of this by the numerator of that. So we're gonna take this over here, and now we're gonna have 7 over 21 plus, we'll take the denominator of this and multiply it by 7 and 3, and that guarantees us, did I do that right? 3 times 7 is 21. 7 times 1 is 7. Right. Okay, good. And now we have a common denominator, so we can add those together, and we end up with 10 over 21, which is the reciprocal of the sum of the resistance of that system, right? And so the R sum is going to equal 21 over 10 ohms. So now it's interesting, right? Because it's not an easy thing like 2 resistors that are the same. so it has to, the electricity is like responding to the back pressure, if you like to think of it like that. So the voltage is putting pressure on this and pushing electricity through the wires, and these are like constrictions. They're resistors offering back pressure, and so the force of the electricity is figuring out where to go. And I think that's very interesting. So 21 over 10 is 2.1 amps. Oh, I just did it again. Holy cats. It's not amps. I must love amps. 2.1 ohms is what this whole system is offering that voltage source. So now we can figure out the amps right here and coming across here and here. So V equals IR, as always. We know the R and we know the V, and we want the I. So I equals V over R equals 10 volts over 2.1 ohms equals, how can I not have that on there? Well, that's what it equals. So that's the current here, but remember the current's gonna split, right? Some of it's going that way and some of it's going that way, and it's splitting based on the resistance that these resistors are offering it. You can do that math real quick if you want to, because that's going to tell you how much amperes you're actually pulling off that battery, which is going to tell you how fast the battery is going to go dead, or if you have a plug-in power source, it's going to tell you if the power source can handle putting out that much current or not, anything like that. So, but now what we're trying to do right now is find the current on this leg and the current on this leg, because one current's going to go that way and some current's going to go that way. And remember, the voltage is the same because it's a 10 voltage drop from here to here, no matter where you do it on that wire, right? So it's just where current equals the voltage divided by R, and we're going to go R1. So the current is 10 volts divided by R1, which is 3 ohms. So 10 over 3 is 3.3 amps. See if I can keep my units straight here. And for the second resistor, we have that, and it's 10 volts, remember? Volts all the way along there, right? And then R2 is 7 ohms. And we get 10 over 7, which is going to be 1.4 amps. And those two are going to add up. So that's got to be 4.7 amps. And you can check me if you want. But 2 times 4 is 8, and we're adding a 0.1 and a 0.7 in there. That seems about right, doesn't it? Passes the smell test. All right. So this is the big deal. This 1 over R, the sum of all the resistances, there's reciprocal of that. 1 over R sum is equal to 1 over each of the resistances in the parallel little parallel system there, and that's how you get the sum. And then you can also figure out the amperage going through each one of those. All right, so now we're going to do one more together, and then I'm going to turn you loose. I don't even know how much time I've done this crazy thing. Where's the timer on that? Holy cow. Have I really been at this for half an hour? That's crazy. Okay, that's all right. So the last thing we're going to do, now we're going to do 3 resistors, because that's where, 3 or more, that's where things get really interesting. 3 resistors. Now we're really thinking about where that electric current is going to go, because all the voltage is pushing the current forward, and all those resistors are pushing back on it a little bit. And so, in fact, I'm going to try and make it even a little more interesting. Not a lot more interesting. So here's our little voltage source, right? And that's still on screen. Is that on screen? Oh, yeah. Let's see here. You can see that. I hope. So that's 10 volts. And now, here's what we're going to do. Instead of a third resistor, we're going to put a lamp. Oh, yeah. Now we are electrical engineers. So there's a resistor. There's a resistor. And there's our lamp. We're going to call this R1. And we're going to make R1 3 ohms. And we're going to call this one R2. And we're going to make this one 7 ohms. And then this lamp, we're going to call R3 because the lamp offers resistance. That's how it ends up glowing, right? Oops, I forgot this part of it. There we go. Now it's a lamp. And so we're going to call that R3. And we're going to say that one has 10 ohms. All right. So we have, there's our system. And we want to figure out, the current here. And we're going to figure out the current. What we need to do is label these places. So I'm going to call this A and B. And then I'm going to call this C and D and E. Because we want to find out the current that's going to go through each of those branches. Because that's going to tell us, if we're designing a circuit, that'll tell us how bright the light is going to be. And if we wanted to make a light with 2 different brightnesses, now we're getting practical. We could design the circuit so that it has a switch where when you switch it, it either runs the current through this resistor and the light bulb, or this resistor and the light bulb. So if you run it through this resistor and the light bulb is going to be dimmer. And if you run it through this resistor and the light bulb, it's going to be brighter. That would be fun. Maybe we should do that. All right, so the first thing we got to do, we want to figure out. So this whole system is going to offer resistance to this voltage potential. The same as always, 1 over R sum is 1 over R1 plus 1 over R2 plus 1 over R3. So it's going to be 1 over 3 plus 1 over 7 plus 1 over 10. And the simplest way to find a common denominator is to just multiply all 3 together. So you got 3. You're going to multiply 7 times 10 is 70. So you go 3 times, and then so you'll put 70 over 70 here. And that's going to be, so that'll be 210. It's going to be 210 all the way across on the bottom. 3 times 7 is 21 times 10 is 210. Oops. That's horrible. 210, 210. All right, so for this one, we need to use those 2 numbers. So 7 times 10, that's going to be 70 over 210. For this one, we need to use these 2 numbers. That's going to be 30 over 210. And for this one, we need to use those 2 numbers. So that's going to be 21 over 210. Whoops. Keep making mistakes. I keep making mistakes my whole life. Okay. So there we go. So this whole thing is going to equal 121 over 210. And then we take the reciprocal to find the actual resistance, right? So R sum, the total resistance there is going to be equal 210 over 121. And that's about 1.7 ohms. So you can see the more resistances you put in here, the more pathways that electricity can take. And it's starting to divide up. It divides up. The resistance of this whole package goes down the more resistors you add, because there's more different places for the electricity to go, right? Okay, so what's the current? So we got V here's Ohm's law, V equals IR. We know the resistance of this whole system is 1.7 ohms. That's 1.7 ohms. Good grief. So, and we know the voltage, so we have I equals V over R equals, voltage is 10 volts over 1.7. Ohms. It's getting late. And I'm going to put 1.74 in there because we wanted to use 2 decimals. Sorry about that. So that's going to give us 5.75 amps coming off here. 5.75 amps. So as long as you got some sort of system that can handle pushing out greater than 5.75 amps, you got no problem. Now we're going to figure out what the current is in each of these places, right? So it's the same thing, right? Current equals voltage over resistance equals, it's going to be 10 volts all the way across, right? And then we just put in each resistor. So that one's going to equal 3.33 amps. And then the next one, I'm going to just sort of move more quickly here. That's 3 volts. That's R1. This is going to be R2, so that's going to be, excuse me, that's ohms. Sorry. That's going to be 7 ohms. 10 over 7 is going to give us 1.43 amps. And the last lamp is 10 volts over 10 ohms, which is going to give us 1 amp. And if you add those up, 3 and 1 is 4 and 1 is 5, 76. That's close enough there. So the last thing I have to show you, and I think I have time, and if I don't have time, you'll have to watch it at home. Let's see, where is my time on this thing? Oh boy. Okay, yeah, we're basically out of time. That's all right. This is today's class, and then I'm going to give you problems. So, the last thing I got to show you is what if you have both, okay? What if you have both series and parallel circuits in the same circuit, which of course you will. It's basically a process of peeling it apart. Peeling it apart. So let's just draw a pretty simple circuit with both parallel and series components. So we've got a resistor there, and then a resistor here, and then a resistor here, and remember, all the components in an electrical system offer resistance. So this seems very generic, but it's realistic. And then there's a really horrible looking resistor there. So we're going to call that R1, and we're going to call this one R2, and we're going to call this one R3, and we're going to call this one R4, and this one R5. So basically what you're looking for, and you're starting from the smallest set of components farthest away, and you're going to look for sets of components that are either in series or parallel. So in this one, the furthest away from the circuit, what do we see? We see a set of 3 that are, this is a set, that's a set that's all in series, right? End to end. So we can do the calculations on that and break it down. And then if we want it, once we've got that kind of figured out, we can do this, and we can just call that, here we go, so here's R1, right? And here's R2, and this, so what we're doing is trying to simplify the circuit. You got to figure this stuff, right? Add up the resistances to figure out what the total resistance is there. And then this is R3 through 5, right? All right, so what do we see next, furthest away? Now we see a system of 2 parallel components. We know how to do parallel resistances, right? We did a series resistance, Now we have to do a parallel resistance, and then this circuit becomes that's R1, and now that's R3 through 5, and we're putting R2 in it, so now that's R2 through 5. We've computed the resistance of this whole system because that is this system which we computed, and now we computed the resistance of this whole system, so that's R2 through 5, and now we have narrowed it down to a simple series circuit. And that is what you do if you have big, complicated circuits. And that's all for today. Thanks, bye.